So for this, probably want to look at the great circle distance for 2 points on a sphere. So let's see if I can convince you of this process. We have a sphere, and the equator is an example of a great circle. A line of longitude is an example of a great circle. But if I have 2 points, there is some unique great circle that goes through those 2 points. Not completely true. Sometimes there's more than one if they're antipodal. But for the most part, this is our example. So imagine I have a point P and a point Q on that sphere. And I find the great circle that connects P and Q. And I'm not looking for the distance, straight line distance from P to Q. I'm looking for the distance on the sphere that we would go from P to Q. And how do we find that distance? Well, what I need to do is I need to go to the center, in this case, 0, 0. That's my origin. And I'm going to construct the vector OP and the vector OQ. And in this example, the radius, spherical radius, is 4. So vector OP and vector OQ both have the same length. Looking at our picture here, vector OP equals 4. And the length of vector OQ equals 4. That is our spherical radius. So my goal is going to be convert points P and Q from spherical coordinates to rectangular coordinates. And then I'm going to use vectors in a way to be able to find that distance. So let's quickly go through that process. How is that going to work? To remind ourselves of the geometry that we need. So here's our first analysis. We have Z here, we have rho here, we have phi here, and we have r here. So looking at this triangle, the cosine phi is adjacent over hypotenuse, is Z over rho, so rho cosine phi equals Z. And I'm also going to need to manage this with r. So looking at sine, yes, sine of phi is r over rho. So rho sine phi equals r. That'll be important for us to use when we go to our second triangle. But let's go ahead and recognize this fact. If we know rho in phi, we can get Z by using this rule that Z is rho times the cosine of phi. Now what's next? Now we're going to go ahead and look at the other triangle. Here's X, here's Y, here's R, and here is theta. So cosine of theta is X over R. So R cosine theta equals X, but what is R? R is, of course, rho sine phi. So rho sine phi cos theta equals X. So that's another rule for us to use. If we know rho, phi, and theta, we can get X using this rule. And then similarly, sine of theta, looking at that same triangle, sine is opposite over hypotenuse. Sine of theta is y over r. So r sine theta is y. But what is r? Rho sine phi. So rho sine phi sine theta, it's r sine theta equals y. So this is the third rule that I need. So what are we going to do next? Think about that for a second. What is our next step of this process going to be? We're going to go back to points P and Q, and we're going to convert rho, theta, and phi to x, y, z. And then we're going to think of OP and OQ as vectors. Here's our point P, and there's the rules that we just established. So plugging those things in, what do we get? We get x is rho 4 sine phi sine pi over 3 cosine theta cosine pi over 6. So we get x is 4 root 3 over 2 root 3 over 2, and we get x is equal to 3. How about y? Y is rho 4 sine phi sine pi over 3 sine of theta sine pi over 6. What is that going to give me? Y equals 4 times the sine of pi over 3 is root 3 over 2. And the sine of pi over 6 is 1/2. So the 2 times 2 is 4, divides out the 4, and I just get an answer of y is equal to the square root of 3. And then we come to z. Z is rho cosine phi. Z is rho 4 cosine phi cosine of pi over 3. Z is 4 times 1/2. So z is 2. So we've successfully converted P from spherical coordinates to rectangular coordinates. So there's the spherical representation for point Q, as well as the rules that we need. So making our substitution here, x is rho 4 sine phi sine pi over 6 cosine of 3 pi over 2. Do we see where 3 pi over 2 is? It's 270 degrees, so that's going to give me 0. So I get 4 times 1/2 times 0. So we get x is 0 here for point Q. For point Y, what do we have? Y is rho, y is 4 times sine of phi, that's sine of pi over 6, times sine of theta, sine 3 pi over 2. So we get y is 4 times sine of pi over 6 is 1/2. Sine of 3 pi over 2, again, 270 degrees, that is -1. 2 times -1, we get y equals -2. And then we go to z is rho cosine phi, rho is 4, times the cosine of pi over 6. Cosine of pi over 6 is the same as the sine of pi over 3. So we get 4 times root 3 over 2. And we get z is 2 root 3. So we've got point P and point Q in rectangular form. So point P is 3 root 3, 2. We have point Q is 0, -2, 2 root 3. So we have the point P and the point Q, and I want to create vector OP and OQ. So vector OP starts at 0, 0, 0. So it goes from 0, 0, 0 to 3 root 3, 2. So vector OP is simply 3 root 3, 2. Similarly, the vector OQ also goes from 0, 0, 0 to 0, -2, 2 root 3. So vector OQ is vector 0, -2, 2 root 3. Now, the great circle distance is a fraction of the circumference of the circle. Remember, the great circle is the same size as the equator. So here's the great circle distance, and it goes back around the other side, right? So I want to find the angle gamma between those two vectors. So remember our rule. Our rule was u dot v is magnitude of u, magnitude of v, cosine of the angle. Usually I would say cosine theta, but I'm going to say cosine gamma this time because the angle between these two vectors is going to be called gamma. So I'm taking OP dot OQ. is going to be the magnitude of OP, which we should know what that is. Think about that for a second. Times the magnitude of OQ. Again, you should know what that is. Think about that for a second. Times the cosine of the angle. So let's go ahead and let's do OP dot OQ and see what we get. OP dot OQ. So we have 3 times 0 is 0. Root 3 times -2 is -2 root 3. Plus 2 root 3 times 2 is 4 root 3. So if we add all those together, then what do we get? What is that dot product going to be? 4 root 3 minus 2 root 3 is 2 root 3 equals the magnitude of OP. Again, we can check it. 9, 3 times 3 is 9. Root 3 times root 3 is 3. 2 times 2 is 4. 9 plus 3 is 12. Plus 4 is 16. Root 16 is 4. But that shouldn't surprise you, right? The radius of this sphere was 4. So the magnitude of OP should be 4. The magnitude of OQ should be 4. We can check that again. 0 plus 4 plus 4 times 3 is 12. 4 and 12 is 16. Square root of 16 is 4 times cosine of gamma. So I get 2 root 3 equals 16 times the cosine of gamma. So we're just about ready to go ahead and get this. If I divide both sides by 16, what is that going to give me? 2 root 3 over 16 is cosine of gamma. So root 3 over 8 is cosine of gamma. So gamma is the inverse cosine of root 3 over 8. And that's approximately how much? Approximately 1.353. So if we know what that angle is, what will the great circle distance be? Think about that for a few seconds. Do we know the circumference of the sphere? Do we know the size of the equator of that sphere? And this is going to be the arc length of a sector. So if I know this angle, how can I find that great circle distance? If you recall the formula for the arc length of a sector, you can go there directly. But I think most people would prefer to first determine the circumference of the circle. So the circumference of a circle is 2 pi times the radius. Now the radius is always the same here, right? We have a radius of 4. Every great circle will have a radius of 4. So the circumference of any great circle is 2 pi times 4, which is 8 pi. So that is the radius of the equator. That would be the radius, excuse me, the circumference of a line of longitude going through the North and South Pole. That's what we get. That is our formula for the circumference of that great circle. Now, we have a fraction of the circle. So how do we find the arc length? I would argue the arc length is the fraction of the entire circle times the circumference. So the arc length is going to be the great circle distance. So the great circle distance is the fraction. So our angle was 1.353. Gamma here was 1.353 radians. Out of how many total? For the entire circle, I would need to have 2 pi radians times the circumference of the sphere, or the circumference of our great circle here, which is 2 pi times the radius. And you're going to notice what happens here is that my great circle distance, my GCD, the 2 pi's divide out. It's just radius times the angle, and that you might remember from pre-calculus in terms of the arc length of a sector. So 1.353 times our radius here, which is 4. And what does that give me? 1.353 times 4 gives me about 5.41. Great circle distance is about 5.41 units.